Hello again. In the previous video, we have already discussed on how we design a proportional controller. In this video, we will discuss a slightly more complex controller and how to design it. The controller is referred to as PI controller, or a combination of proportional and integrative control actions. Before we start discussing on how to design a PI controller, I will take a look first on why do we need a PI controller. Typically, PI controller is designed to achieve two main goals. First, to reduce a steady state error. This is pretty unique to a PI controller. And the second goal is to keep similar, or at least allowing a very small change to the existing transient performance in your system. From the structure, PI controller is not so much different than a P controller than a proportional controller. So in here, GS is the system that you want to control, and GC is the PI controller. In our previous discussion, the controller GC is just simply a proportional gain. It's only a scalar value. But in this particular case, in PI controller, your controller is not simply a scalar value, it's not simply a gain, but there is a dynamic characteristic of the controller itself. What do I mean by dynamic characteristic? So as the name implied, proportional integral controller is a combination of proportional action. This is basically exactly the same like in the proportional controller, where you simply have a gain in your controller. But for PI controller, you combine your proportional action with an integrative action. You still remember 1 over S in Laplace domain corresponds to integral action in time domain. So in this case, this term basically is an integral action with a coefficient of Ki. This PI controller in the form of Laplace function can be manipulated mathematically into this equation. And then if I manipulate it a bit further, I can rewrite it into this equation, right? Now, if I rename Kp as Kc now, and the ratio between the integral coefficient and the proportional coefficient, I call it as Zc. This is now my new form of PI controller in the form of Laplace equation. So if you look at this, our controller now, our PI controller appears as a function of Laplace, which means again it has a dynamic behavior by itself. If we take a look a bit further on this equation, the equation of PI controller, you can easily see that this controller, the dynamics of this controller, will have 1, 0, 1 finite 0 at negative Zc, and we also have 1 pole at 0 value, right? So we have 1 0 pole and 1 finite 0 at negative ZC. If you refer back again on how we sketch a dynamic behavior in terms of the Bode diagram, you can easily see that these dynamics, the Bode diagram will look like the one that I show in the lower right corner of this slide. The upper plot here is the magnitude plot. So the typical characteristic of a PI controller from the magnitude plot is that at low frequency, the magnitude has a slope of negative 20 dB per decade, and at high frequency we will have a zero slope, okay, and the corner frequency will be obviously at ZC. This is a typical magnitude plot of a PI controller. Whereas for the phase plot, at low frequency, it will have an angle of negative 90 degrees until 1 decade below the corner frequency, or 1 decade below ZC, obviously here, because our corner frequency now is equal to ZC, and the phase has 0 degree at high frequency region, above 1 decade above the corner frequency. Okay, and what happened in between, you just simply have to connect these 2 points, and then at the end you will have a line of 45 degrees per decade. You know how to sketch this Bode diagram from our previous video when we discussed Bode diagram sketching. But of course, what you see in this slide, the Bode diagram in this slide, it's only the straight line sketching, the straight line approximation of Bode diagram of the magnitude plot as well as the phase plot. The real plots of magnitude and phase diagrams is not exactly like the straight line sketching, but instead typically the magnitude plot and the phase plot will look like what you can see in this slide now, right? At the magnitude value at the corner frequency or at ZC will not be equal to this point, but it will have a slightly higher magnitude at this point. That is for the magnitude plot, as well as for the phase plot. For the phase plot, at 1 decade below and 1 decade above the corner frequencies, the phase will not be exactly equal to negative 90 degrees for the phase at 1 decade below the corner frequency, and it will not be equal to 0 degree at 1 decade above the corner frequency. It won't be like that, because what we have previously is only the straight line approximation. Instead, in real practice, the phase value at 1 decade below the corner frequency will be slightly higher than negative 90 degrees, while the phase value at 10 times ZC, or 1 decade above the corner frequency, will be slightly below 0 degree. Okay, it won't be ideal as if in the straight line sketching. Now, in the first slide, I have already mentioned that one of the main objectives of designing a PI controller is to reduce the steady state error. When we are talking about steady state error, we always associate it with a steady state errors in terms of system type. You still remember about type 1, type 2, type 3 systems, type 0 system. They have a certain characteristic of a steady state performance. Let's now consider a unity feedback system. So we have a unity feedback system. I don't think I have to draw again the structure of a unity feedback system, but now let's consider we have a unity feedback system, because when we are talking about system type thing is only applicable to unity feedback system. No? Now in this slide, let's consider a unity feedback system then. Now to this unity feedback system, let's consider that we have an open loop transfer function where the equation can be seen in the upper right corner of this slide. In the first case, let's consider a unity feedback system with a type 0 number. So we have a unity feedback system, but the open loop transfer function doesn't have pole that is equal to 0. So there is no first term in the denominator of this GS. If we have a type 0 system, then obviously our open loop transfer function will look like this without this term. This is exactly what I have already written in this part. So this corresponds to the transfer function of GS, where GS is a type 0 system. But now, if I introduce a PI controller in the forward loop part in our unity feedback system, what will happen? Let me draw it again. I think at the end I have to draw it again. So if this is the system that we want to control, that basically this is this transfer function. Initially, let's consider the first case when we have a type 0 system. When we have type 0 system, then this term doesn't exist. We have this system in a unity feedback form like this, right? This is how the system will look like for our type 0 system. But now, if I introduce a PI controller in my unity feedback system, what will happen? This what will happen. I will have this PI controller here now, GC, I will call it as GC. This is my PI controller, where this GC, C, this is supposed to be C, is this form. This is GC. But remember, we discussed the characteristic of a PI controller. PI controller has one pole that is equal to 0, right? So what will happen after I introduce a PI controller in my type 0 system? the type number of my unity feedback system now is increased to type 1 system, right? So by introducing a PI controller, I will upgrade my type 0 system to type 1 system, because I will add one additional integral, additional integrator in my open loop transfer function, right? Now what will happen if we have a type 1 system? With the same logic, of course, this is my type 1 system. Why do I call it type 1 system? Type 1 system is the system where I simply have one integrator. That means n here will be equal to 1. So my GS, my original system, has one pole at origin, one pole that is equal to 0. This is type 1 system. And then after I introduce a PI controller, I will have two poles in my open loop transfer function that are equal to 0, right? That means my unity feedback system now becomes type 2 system. So with the same logic, again, introducing a PI controller, I will upgrade a type 1 system to a type 2 system. With the same logic, again, I don't have to go to detail now. If I have a type 2 system, right, by introducing a PI controller, I will upgrade my type 2 system to a type 3 system. What is the importance of upgrading type number to the system? This is a thing that something that we are going to discuss in the next slide. Okay, to illustrate the importance of increasing a type number in our unity feedback system, let's take a look on the following example. An example on PI controller design. Let's consider a unity feedback system where the open loop transfer function is equal to this one, 1 over s, s plus 10, s plus 20. Okay. Obviously, if you have a system that looks like this, the system where the open loop transfer function GS has only one pole that is equal to 0, and let's consider for time being we haven't tuned the controller, we haven't tuned this controller, so for time being let's just consider GC is a constant gain, a proportional controller with a constant gain of 1. Let's just start it from scratch. We have put this the system GS in a unity feedback form, but we haven't tuned the controller. So for time being, let's just consider GC equal to 1. In that case, then this unity feedback system obviously is a type 1 system, right? We want to improve the performance of this system with an objective. So the design requirement of the controller is that we need to eliminate the steady state error due to the RAM input. So we want to eliminate the steady state error because of a RAM input. Eliminate means eliminate means in this case we want to completely, it's not only reducing, but we want to make it equal to 0 because we want to eliminate the steady state error due to the RAM input. So the first requirement of our controller here that we have to design is that the steady state error due to the RAM input should be equal to 0. That is the first requirement. The second requirement, we need to maintain the stability in such the stability represented by the damping ratio. The damping ratio should be equal to 0.6 more or less. Okay, let's take a look a bit more detail on the steady state requirement. The steady state error due to the RAM input should be equal to 0. Initially, before we design a PI controller, initially we haven't tuned the controller. So let's consider for time being GC is just simply equal to 1. What will happen? We will have type 1 system. If you still remember, for type 1 system, you have seen this table before when we were discussing static error constant of a certain system types. If we have type 1 system, you still remember last time, if we have type 1 system, if you give a RAM input, what will happen? We will always have a finite steady state error. But the requirement, the first requirement of the controller in our example, we need to eliminate the steady state error because of the RAM input. Eliminate the steady state error means the steady state error should be equal to 0 for a RAM input. That will happen only if the type number is at least equal to 2. Okay, so this means again we have to upgrade the type number from type 1 to type 2 system. How do we upgrade it? By introducing an additional integrator in our open loop transfer function, and many ways how we can introduce an integrator to the open loop transfer function is by introducing a PI controller. Okay, so we can upgrade the type number from type 1 to type 2 in order to eliminate the steady state error because of the RAM input by introducing a PI controller. That's the main reason. In the first place, we are going to use a PI controller in our GC here. So we choose PI controller and then with these two requirements, we will design the two parameters in our PI controller. You still remember PI controller, the GC looks like this, right? KC times S plus ZC over S. So for PI controller, we have two parameters that we have to design, KC and ZC. How to design these two parameters? Let's take a look in the next slide. Okay, so in the first place, we haven't designed the PI controller. As I have already mentioned at the beginning, the system, the GS, I have already put it in a closed loop form, in a unity feedback form. but at the beginning I haven't designed the controller yet. I haven't designed the PI controller yet. There are two parameters that we have to calculate to design a PI controller. As I have already mentioned before, there are KC and ZC. Okay, so how do we define these two parameters? We design these two parameters based on the requirement. One of the requirements says that the damping ratio zeta should be equal to 0.6. We are going to design the PI controller here through a frequency response function. In frequency response function, there are few features that we can see from the Bode plot. Those are phase margin frequency, gain margin, and gain margin frequency. Therefore, this requirement we have to translate it into one or more features that we can see from the Bode plot of the open loop transfer function in our unity feedback system. In our unity feedback system. So, how to translate the requirement of damping ratio to one of these features? You can refer to one of the formulas that I have already shared at the beginning of this session when we were discussing Bode plot analysis. I guess it was in the previous 3 or 4 videos. We can translate the information of damping ratio here to phase margin using this formula. Please take a look your lecture note. I have already shared this formula with you. So from this information, from this requirement, I can translate the the damping ratio requirement to a phase margin requirement. Using this formula, I know that the required phase margin now will be equal to 59.187 degrees. Let me change the color. So now the one of the requirements of the PI controller design is to have a phase margin equal to 59.187 degrees. How do we see phase margin? Phase margin is observed from the Bode diagram of the open loop transfer function in our unity feedback system. For that purpose, then in the first place, I have to plot the Bode diagram of the open loop transfer function. At the moment, I still don't have PI controller, or I still don't have any controller in my unity feedback system. So the open loop transfer function in my unity feedback system now only contains this part, right? The GS. So when I want to plot the Bode diagram of the open loop transfer function, I just simply have to plot the Bode diagram of this GS, and this is what I will get. The first plot here is the magnitude plot of the Bode diagram of this GS. The second plot, this one, is the phase plot of the Bode diagram of GS as well. Okay, as you can see, these are the Bode diagram. One of the requirements of the PI controller as we just already discussed, one of the requirements is that the phase margin should be equal to 59.187 degrees. Now let's take a look. What is the phase margin? What is the current phase margin in our Bode diagram? How do we know the phase margin? Phase margin is calculated. Is the distance, phase margin is the distance of the phase from negative 180 degree lines at the frequency where the magnitude is equal to 0 dB. The frequency at which the magnitude is equal to 0 dB will be this frequency. I don't know, this is probably roughly, just looking at this Bode diagram, the frequency will be at 0.01 radian per second, 0.01 radian per second. From here we can calculate the phase margin. The phase margin again is the distance of the phase in our plot, in our phase plot, to negative 180 degrees line. So if this is 180 minus 180 degrees, so the phase margin will be about this. This is our current phase margin. What is this? Probably roughly this will be about 80 to 90 degrees, I guess, right? This probably will be plus minus 90 degrees. This is our current phase margin. While the requirement is the phase margin should be equal to 59.187. So our current system doesn't fulfill the requirement. The current phase margin is about 90 degrees. We need to manipulate this Bode diagram in such the phase margin is equal to 59.187. How to do that? Let me erase this again. We will have a phase margin equal to 59.187 only if this is only if, let me erase this again, please bear with me, I'm using my mouse. Only if the phase margin frequency is at this frequency. If this is our phase margin frequency, what is phase margin frequency? Phase margin frequency is the frequency at which the magnitude is equal to 0. For time being, our phase margin frequency is equal to 0.01 radian per second. This one, 10 power of minus 2. This is our current phase margin frequency. The phase margin frequency is the frequency at which the magnitude is equal to 0. This is our current phase margin frequency. But if somehow our phase margin frequency is equal to 3.7035 radian per second, or it is located at this frequency, if this is our phase margin frequency, then our phase value at this phase margin frequency will be equal to negative 120.813 degrees. At this frequency, we will get the desired phase margin. If by any means this frequency is our phase margin frequency, then we will have the desired phase margin frequency. This frequency, 3.7 radian per second, is a phase margin frequency, that will happen only if the magnitude at that phase margin frequency is equal to 0. So this phase margin frequency equal to 3.7 radian per second will happen only if this point is located at this point, right? This will happen if, in other words, the magnitude plot is shifted up about this size. If the magnitude plot is shifted up about that much, this point will be located at this point, which means the magnitude plot at this frequency will be equal to 0 dB. That will bring a consequence that this frequency will be our phase margin frequency, and if that is the phase margin frequency, we will indeed get the desired phase margin, right? So then we have to shift up the magnitude plot. How to shift up the magnitude plot? How much we have to shift it up? What you have to do, you just simply have to find what is this value. Looking at this magnitude plot, I can identify, I can say that the magnitude at this desired phase margin frequency is equal to negative 58.097 dB, right? We need to in the first place, then we need to introduce a P controller, a proportional controller, to shift up the magnitude plot in such the magnitude plot will cross 0 dB line at the desired phase margin frequency at 3.7 radian per second. How much do we have to shift it up? Of course, because this point is at negative 58.097 dB. This means we have to shift up the magnitude plot about 58.97 dB. We need to shift it up as much as positive 58.097 dB, right? This means we have to introduce a proportional controller with the gain of 58.097 dB, but that is in dB scale. We have to convert it to linear scale, right? So 58.097 dB in linear scale will be equal to 803.3. You know how to calculate this, of course. dB is 20 log 58.0. Sorry, I need to erase it first. 20 log k. 20 log k should be equal to 58.098. From here you can calculate k, and k will be equal to 803.3. That means, in the first place, the first step to design a PI controller, we need to design the proportional gain. We have already calculated that the proportional gain that we have to introduce first to this unity feedback system is equal to 803.3. Okay, now we have the very first step in designing a PI controller. By introducing this proportional gain, we have already achieved one of the two requirements, the requirement of damping ratio equal to 0.6. We still have to fulfill the other requirement to eliminate the steady state error because of the RAM input. How to eliminate the steady state error because of the RAM input? Because currently we have a type 1 system, we need to upgrade it to a type 2 system. That means we need to introduce the dynamic part of the PI controller. We have already I need to put it in a pen. You still remember? I have to write it again here. PI controller looks like this. K or KC is just the gain of the PI controller. S plus ZC over S, right? At this moment, we have already calculated K. K is this one. The last step now, we need to design the dynamic part of our PI controller. So we need to define ZC. How to do that? We introduce ZC to increase the slope at the low frequency, increase the slope of the magnitude plot at low frequency region, right? Why do we want to do that? Because simply we want to upgrade the type number of our system from type 1 to type 2. You still remember again that the magnitude plot of this dynamic, the dynamic part of our PI controller, the magnitude plot will look like this, right? Roughly, the straight line sketching. Negative 20 dB per decade slope at low frequency and 0 slope at high frequency, right? And this is our corner frequency that is equal to ZC. So how to define ZC in this case? To define ZC is very, very simple. I just choose ZC where the 1 decade above ZC is equal to the desired phase margin frequency. If the desired phase margin frequency is equal to 0.3035, this is 1 decade above ZC. Obviously, my ZC then should be equal to 0.37035, right? Again, what I drew here in a green dashed line basically is this magnitude plot. The phase plot of the dynamics of the PI controller will look like this. Okay. In total then, the magnitude plot and the phase plot of my new open loop transfer function, incorporating also the dynamic of this PI controller, will look like what you can see in this black line, right? Where the dynamic part of the PI controller, as we just discussed now, will be equal to, oops, I have to erase this again. See, if you can see it now that my ZC now is exactly equal to 0.37035, My ZC is equal to 0.37035. So this will be the dynamic part of my PI controller. So I will put it again, this dynamic part, in my open loop transfer function. So in total then, these two blocks represent the PI controller that I just designed, right? We are happy here. We have already designed the PI controller. I know the K value. We have already designed it. I know the ZC value. Then technically the PI controller has been designed perfectly. But is that true that we have already designed it perfectly? There is one simple problem here that we just overlooked. What is the problem? You still remember the Bode diagram that we sketched for the PI controller? The Bode diagram that we sketched is simply look like what you can see in this slide, but the real magnitude plot and the real phase plot is not exactly the same as in the straight line sketching. The phase value at 1 decade above the corner frequency apparently will be slightly below the 0 degree line. It won't be equal to 0 degree. It will be something, I don't know, it will be something probably between -5 degrees to -12 degrees. This will bring a serious implication. If we look again to what we just did in designing the PI controller, we designed it based on assumption that the phase value at 1 decade above the corner frequency is equal to 0. That's how we design our previous PI controller. But due to the fact that the real phase value at 1 decade above the corner frequency will be slightly below 0 degree, it won't be equal to 0 degree here. At the end, what will happen? The phase value at this desired phase margin frequency will not be exactly at this point anymore, but it will be slightly below this point, right? It probably the real phase plot will be, I don't know, probably something like this. It won't be equal to this point anymore. What does it mean? This means our phase margin, our real phase margin, will be slightly more than the desired phase margin. So this is the problem that we might encounter when we use a straight line sketching to design a PI controller. We assume that the phase value at 1 decade above the corner frequency is exactly equal to 0 here, but in fact it's not equal to 0. It will be slightly below 0 degree line. It will be something around -5 degrees to -12 degrees, which means again then this will bring consequence that the real phase margin will not be equal to the desired phase margin. So what do we have to do then to mitigate this problem? To mitigate the problem, we have to do it in the very first place when we design the gain in our PI controller. You still remember how we design the gain K in our PI controller in the previous few slides? We designed the gain of our PI controller based on this requirement, the requirement of the damping ratio, and then we translate this damping ratio requirement to the phase margin requirement, right? And then from this phase margin requirement, we define the phase margin frequency that will give this phase margin requirement, right? That's how we did when we designed the gain in our PI controller before. But apparently if we do it like this, there will be a deficit of the phase margin because of the approximation of the phase plot in the PI controller, just like what we discussed in the previous slide. So to mitigate that problem, this is what I can offer to you. When you design the gain of your PI controller, don't use this angle, don't use this phase margin requirement to dictate the phase margin frequency. Don't use this 59.187, but instead use phase margin slightly more than the real phase margin requirement. I will add the phase margin requirement with an angle between 5 degrees to 12 degrees. And then this new phase margin requirement, I will use it to dictate the phase margin frequency requirement. So to make it easy, instead of choosing something between 5 to 12, to make it easy, I will just pick 10 degrees to make my life easy. So instead of using 59.187 degrees to define my phase margin frequency, I will use 69.187 degrees as my new phase margin requirement. It doesn't have to be 69.187. Actually, you can also add it with 10.813 to make it equal to 70 degrees. Probably it will be nicer actually, in fact, right? To make it equal to 70 degrees. Actually, I should do it like this, but anyhow, I have already prepared the slide, so let's stick to this value. My new phase margin requirement now is equal to 69.187 degrees. So how to design the gain in my PI controller? Step by step wise, it will be exactly the same like what we did before. But now what we have to do, we have to find the phase margin frequency that will give a phase margin equal to 69.187 degrees instead of 59.187 degrees. So where can I find this phase margin value? This 69.187 degrees phase margin will occur when my phase margin frequency is equal to 2.4576 radian per second. Okay, so this is how I start. From there, then I can define what the gain of my PI controller is, and then Similarly, I can also define what the ZC of my PI controller accordingly. Okay, so that's how to mitigate that problem. I have my new GC here with ZC equal to 0.2458, 1 decade below the desired phase margin frequency. Actually, if I want to be honest, designing a controller is an iterative process. Once you have already completed this PI controller, in fact, you might want to check once more whether all of the requirements are fulfilled or not. Sometimes you might have a slight glitch here when you check the phase margin frequency, and then when you look at the gain, when you look at the magnitude at the phase margin frequency, apparently it's not equal to 0 dB anymore. It will be slightly deviating from the 0 dB line. In that case, to improve it further, you might want to save the magnitude plot again here about this much. I don't know, probably it will be about 4 dB. You want to shift it down about this much, and then accordingly you can also add another again to improve the PI controller that you just designed. So according to this, apparently if I zoom in this part further, the magnitude value at the desired phase margin frequency is not exactly equal to 0 dB, but instead is about 4 dB. That means I have to bring down my magnitude plot about 4 dB. Sorry, my drawing is not perfect. So the magnitude plot should be something like this. That means, what do I have to do? I have to bring down the magnitude plot of about 4 dB. 4 dB means then the 20 log, let's say I will call it K prime, should be equal to minus 4 dB, right? Because I have to bring it down 4 dB. That means I need to have an additional gain that will bring down the magnitude plot of minus 4 dB. So from here I know that K prime should be equal to 10 power of minus 4 over 20, which is equal to, I don't know, probably this will be equal to 0.63 if I use my calculator. So this means after I calculated this one, I need to add one more gain here, K prime, where K prime now, the value is equal to 0.63. Okay. So this might be my finalized PI controller. Once I have this new PI controller design, I might still want to check it once more for the actual phase margin, actual phase margin frequency, and if everything is okay, then I can stop it there. Again, controller design is an iterative process, so you might want to to do it iteratively to have a better and better design at the end. Okay, Apparently I have already calculated before in my slide. Okay, that's basically then how the controller will look like at the end. And as a conclusion, then my complete PI controller then will look like this. Okay, you can just multiply the 0.6317 with 803.3 in order to complete the PI controller to make it into a nice formula. So that's basically step by step wise in designing a PI controller. Just to conclude then here, commonly a PI controller where the transfer function of the PI controller in general look like what you can see in this slide, Kc times S plus Zc over S, is applied to reduce or to eliminate, depending on the requirement, the steady state error while maintaining or targeting a certain dynamic condition. But the target of the dynamic condition, what I meant here by dynamic condition, is the transient performance. You cannot make a drastic change in the transient performance, but if you want to make a slight change in the transient performance, you can still do it with a PI controller. But the main objective of using a PI controller is to reduce or to eliminate the steady state error. As what we have already discussed in the last few slides, the step-by-step wise in designing a PI controller, typically we started by estimating the gain in our PI controller to achieve first the dynamic condition goal and design the ZC accordingly after that to introduce the integral control effect in order to improve the steady state performance. After you completed it, you might still want to fine-tune again the gain of your PI controller, just like what we discussed in the last few slides. Okay, so that's basically our discussion on how to design a PI controller.